Welcome to Electronic Devices and Circuits Lab. The today's lab we are going to learn a very important circuit of voltage regulator, which is the application of a Zener diode. So first of all, we have to make a voltage regulator circuit using the Zener diode, and then we have to do the measurement of different quantities that will be required for calculation of the percentage voltage regulation. So let's begin the discussion. So first of all, we have to make the circuit. So to making the circuit, we need to bring certain components. So first we have to go to the component tab. So we can go to the component tab here. And from here, we can take the different elements required for making the circuit. So first of all, we have to take a resistance. Okay, I will be taking one resistance. Okay, later on we can change the value of the resistance as per our requirement. Then we need one power supply. So I will be taking a power supply. You just go to the groups. Here you can go to the sources, and here we can take the power sources. Okay, and then we can select one DC power supply. So we have to take a DC power supply over here. Then we have to also select a ground, because ground is always necessary. We have to connect a ground to our entire circuit. Now we have to take a particular Zener diode. So first of all, we have to take a Zener diode. So just go to the diodes. Here you can find Zener diode. So to conduct this particular experiment, I am going to choose a particular diode whose number is 1N4737A. Okay, so I have already seen its data sheet, so you can also look at the data sheet. So its Zener breakdown voltage is around 7.45 volts, and its power rating is around 1.3 watt. Okay, so we can take this particular Zener diode, and then we can have a particular variable resistance. So first of all, let me explain you the voltage regulator circuit. So basically, what we can have in this voltage regulator circuit is basically either our source can be a variable. Okay, we can have like the source can be a variable in which the input voltage may be varying from a certain range. Okay, from a certain minimum value to a maximum value. Okay, and our load which is connected across or parallel to the Zener diode, okay, that will be a constant. Okay, so what is the thing is only input voltage is going to be varying. Okay, so our source is a variable. Okay, so that time this Zener diode has to provide a constant voltage across its terminal to the load. Okay, so load will be connected in parallel to this Zener diode. So this is one of the case for our voltage regulator circuit. In the another case, what we can have is our input may be a constant. Okay, we can give a input voltage which is a constant voltage, and we can have the our load as a variable. Okay, so we can have the load as a variable. So we can connect lots of loads parallel to this particular Zener diode. There may be a 3 to 4, 5 or 6 number of loads. Different loads can be connected. So what we mean to say load over here, we mean to say like we are connecting the lights, fans, okay, any electronic gadgets, any electrical appliances. Okay, anything is going to be connected, that should be connected in parallel to this Zener diode, so that the voltage across their terminals will be a constant. Okay, so what we need to have is we need to have a certain so basically in this particular experiment, either so we first of all we need to understand how many cases are there. One case is that the variable source, the another case is the our source is constant but our load is a variable, and the third case also possible in which both load is variable as well as our source is variable. Okay, but here to conduct this experiment we are taking one of the case in which our input power supply is a constant and our load is a variable. So that condition we have to take for conducting this particular experiment. So let's to have that particular case, what we need to have is we need to bring one resistor which is a variable one. Okay, so go to again component tab and then bring a variable register. So once you will go to this, it is already a basic. So you can see here it is a register, and here we have the variable register. So let us say that we want to take this particular variable register. Later on, we can change the value. So we have this particular register. Now we can close this particular library. Now we have to make the connections, right? So remember that while doing this experiment for voltage regulator, okay, in this case, what we are making is we are making this input voltage as a constant. Okay, I will be calling this source voltage is equals to, I will be making it 20 volt. Okay, and this 20 volt will be remain constant. Okay, and in my table, I will be calling this voltage as E. Okay, so my source voltage will be a constant, and that constant value is equals to 20 volt. Now I will be making this particular resistance value equals to 680 ohms. There is no reason why we are making it 680 ohms. Okay, we can take any value. You can also keep it 1 kilo ohm, 2 kilo ohm, whatever you can make. Okay, first of all, you need to understand the concept. Okay, and basically based on that concept, you can choose your value of this R1 value. Okay, so I am just making it 680 ohms. Okay, you just try to understand the concept. Later on, if you want, you can also conduct the same experiment for different value of R1, okay, which is your source resistance. Basically, it is called as source resistance, okay. So now we have to measure the current through this particular Zener diode, okay. So we want to measure the current through the Zener diode, and we want to connect this particular circuit, this particular variable resistor that will be actually act like a variable load. Okay, it will be acts like a variable load. So first try to rotate this one, okay, so that it can be connected properly. So just you rotate it 90-degree clockwise, control R, you can do it. So now it is rotated. Now we have to make the connections, right? So just you connect this to this resistor, then this resistor should be connected to the this is your cathode terminal, so it should be connected to cathode terminal. Now we have to bring the multimeters. Okay, so just go to this instrument tab, and from here you just bring the multimeters. You please note it down, we have to take multiple multimeters. Okay, because we want to measure the current through the load as well as through the Zener diode, and we have to also measure the voltage across the load. Okay, so we need at least 3 multimeters. Fine. So now we know that the multimeters should be connected in series to the circuit, and voltmeter should be connected in parallel to the circuit. Fine. So now, as you know that the Zener diode, if we look at this particular curve, okay, the Zener diode, when we want to act as a voltage regulator, it should be operated in the reverse bias mode. Okay, it should be operated in the reverse bias mode, and it should enter into the breakdown region to maintain the constant voltage. As you can see from this picture that up to a certain voltage, when we apply the voltage in the reverse bias direction, then the current which is varying, or current which is flowing through the Zener diode is very small up to a certain voltage. Okay, and that certain voltage is called as the breakdown voltage, reverse breakdown voltage of our Zener diode. So once we reach up to the reverse breakdown voltage, then abrupt change in the current you can observe. Okay, an abrupt change in the current you can observe, and the current will increase very rapidly, but the voltage variation will be very small. Okay, the voltage across the Zener diode will be very small, but the current will be varying very abruptly. So that reason is this particular reason is our reverse breakdown reason. And normally, if we want to act our Zener diode as a voltage regulator, then it should be operated within this region. Okay, it should have enter into the breakdown region. Okay, so this can be actually, you can try to get the VI characteristics of this particular Zener diode before starting your experiment. Okay, I have already obtained the reverse biased VI characteristics of a Zener diode. So you can follow my video lecture, okay, previous video lectures, in which I have already obtained this VI characteristics for 4733 this particular diode 1N4733A. Okay, and in this case, the Zener breakdown voltage was somewhere around 5 volts. Okay, and this particular curve we have already obtained. Now, the similar experiment or similar way you can again, if you want, you can definitely obtain the VI characteristics for this particular diode 1N4737A. And you will find that the general breakdown voltage for this particular diode is around 7.45 volts. Okay, so that we are not interested here, but just for the sake of completeness, I am telling you this particular value. So now, after having this knowledge that this Zener diode has to be operated in the reverse bias condition, okay, now we have to complete the circuit and we have to start the experiment. So first of all, we need to connect this multimeter. So just try to make the connections. Okay, so you can make these connections properly. Okay, so just you flip it once so that it will be measuring the current properly. Okay, so now this is a positive terminal, right? So it should be connected to this one. Okay, here you can connect this particular terminal. Now this can be connected to your ground. This can be connected to your ground. So here we can make the connection. You can connect this to a ground. Now, just to try to complete this circuit, this one is connected to here. Now again, this has to be connected, okay, properly in the circuit. You can just bring this a little bit near to this circuit and then just make the connection. Okay, so try to make this connection. Okay, so for making this connection, again you connect this terminal to this one and then you can connect this particular terminal to this one. So once you do this connection, now you can connect this side to this side. Okay, this side. Now this particular voltmeter, okay, it should be connected in parallel. So you can make this connection. Okay, just connect to this point, and the other point should be connected to the other. So now we will be able to measure the output voltage, okay, the voltage across the load. Now, just you confirm that this particular thing is measuring voltage and it is measuring the DC quantity, okay. So I will be calling this output as a VL, okay, output voltage across the load. Now this should be measuring the current. I will be calling it the current through the load, okay. I will be calling it as IL. Okay, so just you select the ampere so that it will be measuring the current. Similarly, they should be also measuring the current, and I will be calling this as a Zener current. Okay, so this Zener current, so just select the ampere. So now we have selected this all proper connections we have made. Now, after making this connection, okay, first of all, what I want to do in this particular experiment is I want to change the load. Okay, I will be varying the load and then I will be measuring the different values of these parameters. Okay, like what is VL, what is IL, what is IZ. Okay, by keeping this input voltage as a constant. Fine. Now, I want this load to vary from, let us say, somewhere around 200 ohms to 10 kilo ohms. So you can see it is written as 1 kilo ohm. It means that its maximum value is 1 kilo ohm when this slider points towards 100%. Okay, whenever it is at 100%, it will be showing like this maximum value is equals to 1 kilo ohm. When it is at 50%, you can say that this value is equals to 500 ohms. Okay, but I want this RL to be varied from 200 ohms to somewhere around 10 kilo ohms. So what I can do is you can just double click and then you can make it 10. Okay, you can make it 10 kilo ohm. And I will make this increment percentage as 2%. Okay, I will be making it 2%. Fine. So after making this, okay, now it is at the 50%. So right now this value is equals to how much? It will be equals to 5 kilo ohms. So just to make it 0. Once you will make it 0, it is equivalent to your short circuit because it is not offering any resistance. You try to understand this one. Okay, it will be not offering any resistance. Now you can verify it by just simulating this circuit. So once you will simulate this circuit, okay, Now you can see that this particular current, okay, this particular current is a current through the load. Okay, this current is 29.41, almost 41 milliamperes. Okay, and the current through the Zener diode is very small in the femtoamperes, very small current. Okay, very small. It is negligibly small. It is zero. Okay, so this current will be equals to how much? It is 20 volt divided by 680 ohms. That you can verify that when it is at 0%, because this is acting as a short circuit now. Now we have to keep on varying this particular resistance value, and we have to fill out this particular table. Okay, this particular table. So what we have taken is, we are conducting the experiment for the voltage regulator. So our diode we have taken as 4737A, and its Zener breakdown voltage you can verify by calculating its breakdown voltage by conducting the experiment. It will be come out as 7.45 volt. So now this is our input voltage that we have to keep it as constant at 20 volts. Okay. Now we have to change the RL, our load resistance value. And that value will be, we have to take as 200 ohms, 400 ohms, 600, 800, 1 kilo ohm, 1.5 kilo ohm, 2 kilo ohm, 4 kilo ohm, up to 10 kilo ohms. Okay. And then we have to measure these values like load voltage. Okay, what is the output load voltage, what is the current through the load, what is the current through the Zener diode. So that we have to measure. So first value is our 200 ohms. So just go to your simulator, and if you make it 2%, okay, you have to just click onto that, and onto the keyboard you can press the right arrow. It will be sliding, the increment will be by 2%. Okay, so the step size will be of 2%. So now when it is at 2%, this value you can calculate, it will be equals to 200 ohms. Okay, now you can simulate this particular circuit. Then you will find that what is this VL is. This is our VL. Okay, the voltage across the load is equals to 4.545 volts. Then the current through the load is equals to 22.727 milliamperes, and the current through this particular Zener diode is 9.583 picoamperes. So this current is very small. You can note it down. Okay, the current is very small. Okay, at this particular moment the current is very small. So you remember this particular picture. When the current is very small, it means that the Zener diode is not yet enter into your breakdown region. Okay, so once the current increases significantly and voltage will be becoming constant, then only it will enter into the breakdown region. So at present your circuit isn't entered into your Zener breakdown voltage. Okay, in Zener breakdown region. So these values we have to tabulate in our this particular table. So I have noted down this value: 200 ohm, 4.545 volts, and 22.727 in milliamperes, and the IZ we have got in the picoamperes. So that value is negligibly small. So I have made it equals to 0. Okay, now we have to make the RL value equals to 400 ohms. Okay, so go to your simulator, just click on to that. You can press the right arrow, it will become 4%. Okay, now you can note it down this value, 7.364 volt. So I have already noted down this value, 7.364 volt. Now you can see what is this current, 18.41 milliamperes, and here it is 0.173 milliamperes. Okay, so noted down these values. So I have already noted down these values. So VL is 7.364, then it is 18.41 and 0.173. Now we can further change the value to 600 ohms. Okay, so go to this circuit again, click onto that, press the right arrow button. It will become 600 ohms. Okay, now you can note it down this value: 7.456, 12.426, and 6.021 milliampere into your table. So these are the values: 7.456, 12.426, and 6.021 milliamperes. Again, we have to make it 800 ohms. Okay, so just click onto that, and then note down the values. Further values you can note down. Okay, similarly, we have to go to 10%. Okay, so that value will be equals to how much? This is here equals to 1 kilo ohm. So after 1 kilo ohm, these values you have to note down: 7.471, 7.471 milliamperes, and 10.945. Okay, these values we have to note it down in this particular. After noting down these values, you can note down that after 1 kilo ohm, the value of RL is 1500 ohms. Okay, this is 1.5 kilo ohms. If you want to vary with the 2% of a step size, no issues, you can go. The number of readings will be increased, nothing else. Okay, so to just directly jump on to the 1500, it will be equals to your 15%. Okay, so what you do is go to your circuit, you can double click this one, and you can make this increment size 5%. Okay, so once you will make it 5%, okay, first of all we need to stop this simulator. Okay, double click this one, and then you okay, so it is 5% now. So now you can run this simulator and just click onto that and press the right arrow. Now it is 15%, so it is equals to how much? It is equals to your how much? It is 1.5 kilo ohms. Okay, so now you have to note down these all values. Just to see these values, and then you can note down these values into your table. Okay, so these values we have noted down. Now again you go back, and then we have to measure this value for 2 kilo ohms. So just go to that. Again you have to click onto that. Then again we have to measure for 2 kilo ohms. We have to note down these values. Similarly, all others values have to be measured. Okay, you can keep on varying. You can measure 4 kilo ohms at 40%. Then at 60%, you can measure the 6 kilo ohm. Okay, RL will be equals to 6 kilo ohm. Now you can make it 80%. It will become 8 kilo ohms. And finally, you can go to the 100%. It will become 10 kilo ohms. Okay, so for the 10 kilo ohms, you can see this result 7.484. 748, this becomes 748 microamps, so it is 0.748. Okay, so the load current, okay, that load current becomes very small. Okay, you can see that the load current becomes very small, 0.748 microamperes, milliamperes. Okay, so that is the value. This is the real value, and this is our current through your Zener diode, 17.658. 17.658. Okay, so after doing this experiment, okay, we have got this particular table. Okay, we have already got this particular table. So generally in the case of voltage regulator, okay, one of the parameter is very important, which is your percentage of voltage regulation. Okay, so generally we ask to find out what is the percentage of voltage regulation that your regulator is able to regulate. Okay, so this is defined as percentage of voltage regulation is equals to V at no load minus V at full load divided by V at full load multiplied with the 100%. Okay, so first of all, try to understand that what is at no load condition and what is the full load condition. Okay, so in the no load condition, first of all, you see this circuit. Okay, if you see this particular table, okay, you can see that when the resistance was minimum, okay, when the resistance was minimum, the load resistance was minimum, at that time the circuit is load is drawing the maximum current. You can see this. Okay, it is 22.727 milliamperes, so it is drawing the maximum current when load was minimum. Similarly, when the load is increasing and when the load is reaching to 10 kilo ohms, at this time the load current is minimum. Okay, you can see that load is drawing the minimum current. Okay, load is drawing the minimum current. Okay, here you can observe the voltage variations. Okay, here you can see that here the voltage was 4.545, and then it is suddenly changing to 7.364, and then the voltage is changing very slowly. Okay, because it has already entered into the Zener breakdown region. Okay, so you can see the abrupt change. Okay, abrupt change you can see. So basically when we talk about the no load condition, voltage at no load condition, the meaning is that the load is not drawing any current. Okay, when no load is connected, okay, the load is not drawing any current. Okay, so you can see that if we want to calculate what is the output voltage across the terminal of the Zener diode when no load is connected. So no load connected means your load is not drawing any current. So how to obtain that voltage? To obtain that voltage, obviously we want to calculate, there is a load which is connected over here. Okay, so if you disconnect this point, okay, If you disconnect this point, then obviously this load is not connected and no current will be flowing through the circuit. Okay, no current IL will be becomes 0. So this is our no load condition. We have not connected any load. Okay, and then you can start this, you simulate this one, you will find this voltage, this particular voltage is equals to 7.485. Okay, you can see that the load current is 0. Okay, entire current is passing through your Zener diode. Okay, the Zener diode is passing through this particular, okay, entire current. Okay, because load is not connected, so it is no load condition. Okay, and this no load voltage is 7.485. So you can note it down, this value here. The voltage, no load voltage is equals to 7.485 volt. Now when we want to calculate the voltage, okay, corresponding to full load, okay, then we have to try to understand here. Sometimes the people or the student get confused that the full load condition may be equals to when the RL is maximum. Okay, but this is not true. Okay, the full load condition is the condition when the circuit is drawing the maximum current. Okay, when it is extracting the maximum current. To try to understand the concept of your voltage regulator, you try to understand lots of loads will be connected in parallel. Okay, so you know that if let us say there are total 5 loads are connected in parallel, and all the loads will be offering you a certain amount of resistance or impedances. Okay, so whenever you are connecting a particular load, let us say if you connected up only one load, okay, and all 4 loads are open, in that case only one resistance will come into the picture. Once you connect the second load also, if 2 loads are connected in parallel, then there will be a resistance offered by the first load and then another resistance offered by the second load. So the total resistance offered by this parallel combination will be smaller. Okay, similarly, when your 5 loads will be connected, the total resistance of this resistances connected in parallel will be very small, and that time it will draw the maximum current. Okay, so try to understand this concept. So what we are saying is, we are saying that this particular full load voltage, okay, this full load voltage will be the condition when the RL is smallest. Okay, the RL is smallest and corresponding VL will be equals to your full load voltage. So what we can say is, because at this time it is drawing the maximum current, you can see if the full load voltage, let us suppose that if somebody is telling you that your voltage regulator is having the RL variation from 200 ohms to 10 kilo ohms. Okay, then you can just talk about the 200 ohms. Okay, because what can happen is you can turn off all the loads, and when you turn off all the loads which are connected in parallel to this particular Zener diode, then no load will be drawing the current and it is corresponding to the open circuit condition. Okay, and that will be equals to your no load voltage, which is equals to 7.485. So it will be always be a constant. Okay, that you can calculate in this way. But when you want to calculate the full load condition, you have to know what is the minimum resistance that your parallel circuit is going to offer. Okay, and what is the maximum current that your load is going to draw. Okay, so that is equals to your 22.727 for this particular case. Okay, if our RL is varying from 200 ohms. Okay, so when it is varying from 200 ohms, so if we consider this 200 ohms as my minimum load and it is drawing the maximum current. Okay, so it is the full load condition. You try to understand this concept, it is very important. Okay, so at this point it is drawing the maximum current and I will call this voltage equals to the full load voltage. Okay, so this value is equals to 4.545 volt corresponding to RL equals to 200 ohm. So if you calculate the percentage of regulation, okay, voltage regulation by following this particular formula, you will be getting, you just try to do this calculation after substituting these two values, you will be getting the 39.28%. Okay, you remember that this value is very high. Okay, if you have already studied about the voltage regulation, then you remember that ideally the voltage regulation percentage of the voltage regulation should be 0. Okay, it should be 0. It should be 0. It should be minimum. Okay, then only your voltage regulator is acting as a perfect voltage regulator. Okay, why? Because what we want is whenever the current drawn through the circuit, if our load is drawing the current, there should be no variation in the output voltage. Okay, okay, there should be no output voltage variation. But here you can see that it is 22.727, it is 4.545. When it is 18.41, then the voltage is changing a lot. Okay, here you can see the voltage is changing a lot, and after a certain point the voltage is remain constant. See, 9.33, the current is changing 9.471, but this voltage is remains constant. Voltage remains constant. Voltage remains constant. Okay, so it should be a constant voltage. There should be no variation across the voltage of the voltage, okay, across the load. So this is the concept. So once you calculate this one, this will be the percentage of voltage regulation. And let us say that if this variation of the load was from 400 ohms to 10 kilo ohms, then your full load voltage will be corresponding to 400 ohms. Okay, so that value is equals to 7.364 volt. So that you can calculate the percentage voltage regulation. If you calculate from this formula, you will get this value equals to 1.616%. Okay, so I hope how to calculate the voltage regulation, percentage voltage regulation, and how to perform this particular voltage regulator circuit, how to perform this experiment must be clear. So try to conduct this experiment by your own. I hope you will be able to do this experiment. So thank you for watching. For any doubts, you can drop me a message. Thank you for watching.